This time on Engine Masters, we are living the tunnel ram life and showing you what camshaft lobe separation angle is all about. Whoa. That was the bad one anyway. Me and the Steves love testing engines, and in particular, we love testing camshafts because there's always something to learn, and this time we're going to address one of the most complicated things about camshaft profiles, and it is lobe separation angle, or lobe displacement angle, also called LSA or LDA. First, let me tell you what that's all about, and we'll do it staring at this 440 Mopar camshaft by Comp Cams right here. So the forwardmost lobe on the cam is the exhaust port on this Mopar. It's opening and closing the exhaust valve. The third one back is the intake lobe for opening and closing the intake valve. Look at them and you can see that there is an angle. So if you draw an imaginary center line between the peak lift of both of these lobes, you can see that there is an angle between the two. When you have a tighter lobe separation angle of 106 degrees, the exhaust events all happen later. The intake events all happen sooner. The opposite is true when you spread it out to a wide lobe separation angle. At that point, all of the exhaust intake and closing events happen earlier, and all of the intake happens later. So there's a lot of voodoo that has to do with this, and as a matter of fact, if you have a dual overhead cam engine where you've got one stick that's got the intake lobes and one of them that's got the exhaust, you can move that stuff all over the place independent of each other. We're gonna keep it very simple for this test. We're gonna run 3 different lobe displacement angles, 106 degrees, 112 degrees, and 118 degrees. So what we've got there is 106 is tighter. It's closed up like that. 118 is really wide. It's spread open like that. And so we got Comp Cams to make us 3 separate camshafts that are identical except for the lobe separation angle. They're all mechanical rollers. They all have a duration at 50 of 264 on the intake, 268 on the exhaust. The lift is 660 and 330. That lobe separation angle again is 106, then 112, then 118. So let me talk a little bit about what you can kind of expect from this, which you might not see on the dyno, and that is idle quality. When you take that lobe separation angle and tighten it up, it makes for a lot of valve overlap, which is the period of time that both the intake and the exhaust valve are open at the same time across the end of the exhaust stroke and into the intake stroke. That's what gives a camshaft that really choppy idle. It makes it sound gnarly, but it also reduces idle vacuum and can make drivability difficult. So that is the cost of the tight lobe separation angle. However, it tends to make much beefier mid-range torque. When you widen out that lobe separation angle, you smooth the idle. You get greater vacuum, and that's the reason you see it in a lot of VFI applications. And the other thing that you do with that wide lobe sep is it tends to favor the much higher end of the RPM curve for the camshaft at the sacrifice of mid-range torque. So our plan is to run those 3 camshafts through that 440 Chrysler. And to tell you all about that, the beauty is on duty. Mr. Steve Dulcich!
All right, put me in the Wayback Machine because I actually built this engine 20 years ago, and honestly, it hasn't been apart since then. Let me give you a little detail about the whole combination here. Most of the stuff is really stock passenger car equipment. I've got a stock 1969 block, I've got a stock Ford steel crank, and I've got 67 440 heads, which I ported. Now, the block is filled with some high-performance parts to add durability and performance. I've got Eagle H-beam rods. I've got Arius pistons, which give me 12.66:1 compression with these cylinder heads. The bottom end has a Mylodon stud kit, a Mylodon deep sump pan, and a Mylodon tray. Now, the real beauty of this engine is sitting right here, the glorious Wyand high ram tunnel ramp. I used this engine for all kinds of dyno tests for magazine articles, and one of the things I did was test a 4150 4-barrel combination, a Dominator setup with a single carb, and this, my tunnel ramp. And the tunnel ramp pretty much put everything else to shame. So we're gonna roll this thing into the dyno, With the 106-degree lobe separation angle, we're going to see what kind of power that makes, and we'll compare it to the other two camshafts. And more importantly for me, I get to see if it still makes the same power it did 20 years ago.
The only thing I know here is that I'm going to get smarter by the time we're done. I've done this test before, but I think not knowing as much as I know now, so I'm going to be able to look at more things and think through more camshaft event processes and get smarter.
And have more questions when you're done.
For sure. Every single time.
Always the case.
And I'll have way less anxiety when we're done.
Are you still all torqued up?
Dude, yeah.
My favorite part about this episode, he's in charge of the mechanical stuff.
Oh, perfect. Yeah, but he's all freaked out. Every time Dulcich has his own engine on the dyno, he gets all twisted.
Why do you guys like it so much when I'm actually feeling a lot of consternation? I mean, why would that give you pleasure and joy? Seriously, I mean, we're all friends. We've been working together for a long time.
It's just the total reaction, and bringing you back down is really the fun part, telling you that it'll be okay.
I'd actually like to put this in a car now, but Steve, why don't you just put me out of my misery and get this test over with?
That's a good idea.
I can do that.
All right, we're going to fire it up initially with the camshaft with 106 lobe separation angle. So we're going to see big horsepower and find out what it makes on the 106. First of all, Dulcich, that's a stout iron head 440.
Yeah, I know.
It runs pretty good.
Yeah.
All right, here's our power numbers. It made 664.9 at 6,300 RPM, and I'm going to allow Dulcich to call that 665.
Oh, thanks, buddy.
And 614.1 pound-feet of torque at 5,000 RPM. And I did the math. That's 1.36 pound-feet per cubic inch, which for 452 inches with an iron head is like pretty wowzer.
The iron head part's the most impressive.
Yeah. I mean, the tunnel ram's contributing to that, and so is the 12.66 to 1 compression for sure. But still, to be able to even move the air through that small block head that they installed on 440s is not bad.
Not just iron, but actual original equipment production iron head.
It's a 67 440 cylinder head.
And Steve put his magic in.
Oh. Boom. So we're going, this is 106, and we're about ready to go 112. So we're spreading at 6.
Yep.
All right, here we go. Cam swap. Brulé's going to watch. Dulcich is going to change, and I'm going to surf Instagram.
You can get that, Troy. You're strong as an ox.
Look at this. This is supposed to be a press fit, but Dulcich honed it so that we can do the swap really quickly. Nice.
All right, it did better than I thought. Because a lot of times when they heat up, they get stuck.
Yeah. A bunch of people have asked me what the point is of this unit right here, which is the Jessel, which is the brand, camshaft belt drive. People have seen this on that other big block that we were running, and on social media they asked me, you know, what's the point of that? Does it make more power? Theoretically, supposedly, the rubber belt instead of the chain transfers less crankshaft harmonic to the camshaft. Does it matter on this? I don't think so, especially at an engine at this level. Maybe if you're running some pro stocker with all kinds of valve spring pressure, it's a different story. In this case, it's super handy for us because you can change camshafts more quickly, and it's got just an adjustable slip in it so that you can degree the camshafts like that. Do you agree with this, Steve?
Absolutely, yeah.
Okay.
So the convenient thing from a testing standpoint is a lot of times that's part of the process. We'll swing the camshaft forward and back a couple of degrees to see what the engine actually likes and optimize the tune-up with it.
Yeah, it just makes it super easy on cam timing is the main reason we run them. All right, now you just pull these out and cam out. That's a big time saver. These are good cams to keep too.
Yeah, they are.
Stabbing in the 112-degree lobe sep cam.
All right, that's it. The engine's all back together. We've pulled out the 106-degree lobe separation angle cam, and we went with a 112. That's a big change, but we want to see a big difference. So we're going to take a look at what that does to the power curve.
Well, looking at the peak numbers, we just made 660 horsepower at 6,400 RPM and knocked the guts out of the torque at 587 pound-feet at 5,100.
Really?
Yeah, but this isn't going to be a story about peaks. This is going to be a story about shape of the curve. So let's have a look at the graph.
Boom.
Oh!
Wow.
You would not choose to do that.
No, and that's what I was saying. It's just different modes, but the OEMs do it for idle quality and smooth and low emissions and no overlap and all of that.
You mean OEMs run wide lobe separation angles for all of that?
Racers do it for stuff out here where this engine doesn't run.
Right.
And so all this is to me is just a loser.
So I think the other reason that we run them on big blocks is that we're running such a big lobe that when you spread it wide, you've still got overlap.
Well, or less overlap with the larger lobe. Right?
Less overlap? No, what I'm saying is
when you spread them out.
Yeah, but obviously if you took the same cam and ran it narrower. But the lobe is so big that when you say it's on a 114, it's still got a ton of overlap compared with what you would do with a smaller lobe.
Yeah.
The smaller the lobe is, the more radical the change is on lobe separation angle, the effect on overlap.
Yeah, no, there's still a lot of overlap with the larger camshafts. But again, most of the time when you're looking at a camshaft that big, and whether it's a big block or a small block, the thing's revving up to 8,000 or 8,500 RPM. You're not trying to take advantage of a 112 or 14 lobe sep at 6,500 or 7,000.
Right.
You're looking for that advantage up higher.
I've been playing in that neighborhood so much recently that I forgot why when you flip through the cam catalogs, all the drag race cams are on a 106 or a 104 or 108. And that's why, because, I mean, we just killed this thing.
Well, even more so when you look at the catalogs, you'll see circle track stuff on 106s and that sort of thing because they want the torque coming out of the corner.
Wow, that's more dramatic than I was hoping for.
No, but that's okay because when I originally built this engine 20 years ago, the lobe sep I went with was 107.
Yeah.
Because I knew it was a production-based cylinder head, and it's a small cross-sectional area, so it's airflow limited at that displacement. Now, if I was doing a 383 with the same head, it might want to go a little bit wider and still be okay and run out the back door at a higher RPM.
Because of the RPM capability?
Yeah, the airflow to displacement, basically.
Okay.
So
I remember about 100 years ago, I remember a 360 cubic inch sprint car guy saying he was putting a 106 lobe sep cam in and that should help it out of the corners. And I just didn't grasp it.
Right.
This sure helps. This is real visual.
It's interesting because when I was completely ignorant of all this stuff, instead of just mostly ignorant about all this stuff, I used to think, I thought because drag race cams for small blocks and stuff, they are on 106 and 108, and, they idle really ratty. I thought they were for RPM. It's not. That big overlap actually is for torque.
Mid-range. It comes on the cam.
Mid-range.
When it comes on the cam, which is where things tune together and it just gets that boost in torque right there in the mid-range.
And Comp Cams always does their shelf, not always, most of their shelf cams are on a 110 for a typical street strip engine. And I think that's for a balance between idle quality, because a 106 is ratty and lumpy and messy, and still making some of that mid-range power.
I think a 110 is probably, as far as a compromise, it kind of catches everything.
Okay.
You're not giving it away as like a 112 or 14 and getting very specific, and you're not getting that horrible idle like on a 104 or 106 or something. So a 110 is really a great compromise. But when you get more specific and the application and you learn a little more about this stuff, you start to look for those little small changes that you can make to enhance the performance of your application.
What I'm hearing a lot on this is that, unlike some of the other things that we do with camshafts, that in the world of the engines we deal with is fairly universal. Like you add duration, you add RPM, kind of. You advance the cam, you get more low end. You retard it, you get more high end. Those are like general rules. But what we're doing here with the lobe separation angle seems, based on what you guys are saying, to be more engine specific.
Oh, absolutely.
Yeah. So
and application specific.
Yeah, making it a bigger problem for the average guy to decide what to do, which is why you just default to 110. And this engine's kind of a tweener. It's not a normal street strip engine. It's weird because it has compression and a tunnel ram and a tiny cylinder head that you've improved. So maybe it wasn't the best thing to actually do this test on. Maybe we should have done it on a more typical engine.
You know, I've seen the same test with a 350 or 383 Chevrolet and 10 1/4 to 1 compression. The results are really just very similar. I mean, these characteristics and, like you say, the engines that we typically deal with that's kind of the outcome.
So this is 106, this is 112. Is 110 going to be right between these two?
Yeah.
That's what happens.
Yeah, pretty much. Okay, I think that was the meat of the episode, and now we're going to move on to seeing how much we can actually ruin Dulcich's 440.
How much power can we lose?
With 118. Let's go make it worse. Another cam swap coming up.
Can we run the cameras backwards and then finish with the, with the other cam? What I'm doing here is putting on the push rods. And here's a little tip, because if you just put the push rods in, they'll drop down out of position. But the simple trick here is just to put a little piece of welding rod across the rocker stands, and that'll build them up to just about the perfect height. You can drop the rocker shaft assembly on, and the whole thing is ready to tighten and go. So you don't want to just like ramrod any of the 5 bolts holding the shaft down. That's going to stress the shaft because some valves are open or some rockers are going to be engaged. So you want to just kind of ease it down that way so you can avoid damaging the shaft.
Okay, I think we're done. Ready to go fire it up and find out how much power this camshaft kills. All right, Dulcich, brace yourself for disappointment.
No way, man. It might be the magic cam. The 118 might be the key.
We're going the wrong way on this episode.
I don't think so.
Well, our peak numbers here are once again destroying the torque curve. 575.2 pound-feet of torque at a peak RPM of 5,300. And the horsepower is basically the same, 659.9. Call that 660 at 6,500 RPM, which tells you why you never want to believe when somebody just tells you how much horsepower that their junk makes. Never trust engine masters when they only talk about horsepower, because we're about to show you why that's not the only thing that matters. There's the curve right there with our 118-degree lobe separation angle camshaft. We're going to overlay it with the 112, and there you go. The 112 is in red, and yeah, it's...
See, that's a trend we were talking about. Up here, where the street engines are kind of done, is when the super wide lobe separation angle may actually start to have some advantage.
Well, it did actually raise the RPM at which peak power occurred by a couple hundred RPM.
It did. So you're saying if this was a 327 with a good cylinder head on it and you were going to run it to like 8,500 RPM, this might be the right thing to do?
Yeah, if you didn't care about anything it did below 6,500.
Okay, yeah.
You'd run it from 65 to 85. Yeah, it might be the right thing to do.
Yeah. Okay, now to show you just actually how devastatingly bad this really is, let's compare it to the 106-degree lobe separation angle where we started.
Oh, wow. You'd like that.
So clearly, the blue lines here are the best camshaft with the 106.
Look what it does here, though. With each step of wider lobe sep, it starts to carry a little bit better up here where we're not using it.
Why did it only float the valves or have a valve spring issue with the 106 cam?
I think the springs warmed up after Dulcich leaving the engine sit there for 10 years.
That's possible.
They've rejuvenated themselves.
It's actually possible.
The real meat of the story here is like right off the hit at 3,500 up through peak torque. I mean, it's just free power down there.
Up through peak torque. How about up through peak horsepower?
Well, okay.
It's all the way.
All the way.
All the way, that tight lobe separation angle's a win. And as disappointing as this was to go backwards in the power curve, the average power the whole time, it still taught me something. Because I'm still rolling around in my head the whole concept of like when you would want to pick something that has a really wide lobe separation angle versus when you wouldn't. We haven't talked about idle quality. We haven't talked about if you have EFI and you know, are more comfortable tuning it with a better idle quality, which you get with the wider lobe separation cam.
Idle quality, vacuum signal, all the things that EFI wants. That's part of the reason. Probably part of the reason that we see it in factory camshafts now versus, or in the fuel injection era versus muscle cars, 60s, 70s era stuff.
Well, and also the newer cars have much better cylinder heads than they did back then, which is why they can get away with those camshafts. It really speaks to what makes the LS so good.
Yeah.
Is that it can be, the combination of a great head and a small cam with a lot of lobe separation.
And then what about runner length, too? How is that going to affect it? You know, that's kind of a question mark still, but I would say the correct lobe separation angle is really specific to your combination and your RPM range.
Absolutely.
I mean, we can't walk away from this and just say, oh, you want a super tight lobe separation in every case.
No, in fact, there aren't even, this is what I was saying earlier, there isn't a general trend that we can say. Like with duration, you can say you add duration, you increase your RPM at peak horsepower. You know, it pushes the RPM up pretty much universally until you saturate the cylinder head or whatever. But with this, it's really engine specific.
You guys have driven stick shift cars with type lobe set camshafts, right?
Yeah.
Right.
And they
aren't they freaking miserable? I mean, it's just like this all the time. So there's a good reason. It's just for drivability.
Wow, that is an eye-opener, though. I mean, this test went too far on the wide. I would have rather seen us go like 102, 106, 112. The 118 is just off the plot.
But I think it's good for demonstration purposes. I mean, I think it shows us what the trends are.
All right. Let's get this baby off the dyno and sum it up, Freiberger.
Let's get this baby off the dyno and get that 106 cam back in it stat.
I know.
Absolutely.
Okay, Steve, with every test, we progressively castrated this thing more and more and more.
Oh, you know how to hurt a guy.
So I want to throw it back to the beginning to give you credit for making 660-something horsepower out of stock iron heads on a 440 with a stock stroke.
Well, thanks for the kudos, Freiberger.
It's really good.
I do appreciate it. I was pretty satisfied with that number.
It was great. Yeah. I wasn't that satisfied with our camshaft testing results. I always have to scale my comments about these tests down to what I think is the average street strip muscle car guy with an engine like this. In other words, we're not dealing with Formula One or Pro Stock or even a guy trying to run eights. It's a guy who's got anything from a daily driver to a 9-second muscle car.
Okay.
In that range, I would say pretty much get a camshaft with a 110-degree lobe separation angle, maybe a 108 if you're drag racing.
Right.
If it's a dedicated drag race car and it's only going to run up to about 6,500 RPM, get the 106.
Right.
I think that there's no real call for getting anything really wide, like a 114 or something, unless you're dealing with an LS engine with a fantastic cylinder head, or unless maybe you want really great idle quality with EFI.
Yeah, or if you've got a very, very high-performance car or boat or something where you're revving it out to 7 or 8 grand.
Oh, that's when you would use a wider one, yeah, if it was really above 7 grand.
Another validation besides the horsepower, when I first put this together, and I used a comp roller cam back then, which is quite similar to what we tested today, I picked 107.
Oh, did you?
Yeah.
Yeah.
And it made almost the same power as our 106. So there you go.
So there you go. I didn't learn a lot from the data that we actually saw here because we just kept on killing power. But I think it was definitely representative of the fact that you can go way wrong with lobe separation angle. And if you've got a question, basically pick the camshaft out of the catalog, look at the description. They've done a pretty good job of keeping you out of trouble. Comp cams for the win, and the Dulcich 440 tunnel ram motor for the win. How cool is this guy? I'm gonna see how happy you are when this thing makes like big power.
I built this 20 years ago, Freiberger. Do you realize that?
It didn't break sitting in your garage.
Yeah, that's true. I haven't run it in 10.
Might have rusted.
Yeah.
Yeah. Well, we've already tuned it up a little bit, so we know the 440 runs. So you should have seen him off camera like, 3 hours ago. It's just like, one cigarette off the end of another, one beer off the end of another.
I guess it would be horrible for me to admit that I was enjoying it just this much.
I know. This time on Engine Masters, Motorhome 440, iron versus aluminum heads, and turbo. It's time for more fun with 440 power. So between Roadkill and Engine Masters, we have really turned the Dodge Motorhome 440 big block into a cult superstar. Think back to Roadkill when we built that General Mayhem 68 Charger and tore a 440 out of a motorhome to install in the car. Later on Engine Masters, Dulcich took the 440 that was in the dirt everyday Winnebago and cleaned it up and hopped it up. And between episodes 53 and 58, we ended up making 392 horsepower with a stock long block. And that was pretty good. Now we're going next level by backing up to begin with, because I assure you, this particular turd will not make 392 horsepower. This one's more worn out than our other ones that we've had. It's from a 1978 Dodge Crew Cab truck. This thing has like 7.2 to 7.4 to 1 compression ratio. Everything about it is stock with the exception of a Comp Cam's XE268H flat tappet camshaft and the valve springs to match. It'll have headers on it. It has an Edelbrock base performer intake manifold and a Holley 750. Now, what's gonna make this episode great is you're gonna learn a whole lot. First of all, we're gonna turbocharge it, because people keep telling us without low compression, it's built for boost. Well, we're gonna find out just how built for boost it is. Second of all, people keep asking me, how much better would those engines do if you put aftermarket cylinder heads on it? And we're gonna do that as well. So here's the program. First, we're gonna run this thing naturally aspirated as it sits right now. Second, we're gonna add a turbocharger. Third, we're gonna bolt on some Trick Flow Specialties aluminum cylinder heads. And then fourth, we're gonna add a turbo with the aftermarket heads. So look at all the stuff that you're gonna learn. How much does a turd bone stock 440 make with a cam intake and headers? Then you're gonna find out what you can do with a cheap turbo setup. Then you're gonna see what kind of power the aftermarket heads make naturally aspirated. And then you're gonna find out how much power it makes with a turbo and aftermarket heads. It's the episode that just keeps on giving. I should begin with an apology
For
bringing that into your shop.
you deserve to apologize. That engine is responsible for single-handedly changing Westech's policy on junkyard engines.
What's that?
They don't come in the door anymore without hitting the hot seat first.
Oh, okay, grease pit.
That thing was hideous. I mean, there was literally chunks falling off of it. So.
Yeah. Steve's OCD, so he cannot handle a drop of oil on the floor, much less that turd. This thing, unfortunately, isn't going to make the power that yours did before, so you'll be happy to know you're going to win that.
Well, okay.
Yeah, it's a bit of a smoker, but we can fix that with the turbocharger. First, though, we're going to run this thing naturally aspirated and have a look at the baseline number. Ready?
I'm curious.
I'm gone.
Yeah.
Yeah. Wow, it's better than I thought.
Here's our baseline power, kind of what's expected. 447.7 pound-feet of torque at 3,500 RPM, and an even 350 horsepower at 4,900. Now, the last time we did a Motorhome 440 was episode 58, and it made 392 horsepower. But some things were different. You had that thumper cam in it that had a narrower lobe separation and more exhaust side, and we had degreed it to perfection, and it had a performer RPM intake manifold instead of the base performer, and it didn't smoke like this one.
I think I had a street dominator, single plane, for the 392 horsepower run. Yeah.
Okay, maybe that was it, yeah. But nonetheless, a slightly different combination, which is why this one's down.
it also had the magic touch of the dulcich. You forgot that part.
Okay, the next step is something I didn't really anticipate initially. We're gonna go install a Holley Street Dominator intake manifold, which is a single plane, because that's the unit I wanna use for the turbos later. So we're gonna do an A/B test on the Performer dual plane versus the Street Dominator single plane. Yeah.
Makes sense to me.
Yeah. Let me go get it out of my Jeep. Okay, here we come. This intake right here is the first intake manifold I ever purchased. I got it at the street races in about 1986 for 50 bucks out of the trunk of some guy's car. So if it's hot and somebody has a stolen intake manifold over the past years, I apologize. There we go, Holley Street Dominator. Now this is a single plane intake, which normally means it would throw away a lot of bottom end torque, but this has unusually long runners for a single plane, and dulcich says it's gonna make more power everywhere, but that's what we're here to find out. So Steve's gonna fire it up, and we're gonna watch. So our new peak power numbers are 444.5 at 3,600 RPM and 364.8 horsepower at 5,000, but that's not the whole story. Here you've got the red line being the Edelbrock Performer intake, the black line is the Holley Street Dominator, and I'm calling this a trade-off I would make.
Yeah, absolutely. This, like Steve had mentioned earlier, the converter will eat that up. You're right past that RPM almost immediately, and this is good stuff here.
That carries pretty good. I mean, I think that's entering the realm of real muscle car madness.
Think so?
Well, 365
horsepower.
That was an advertised number for a lot of legit muscle cars.
10 away from a 396. Yeah. Not bad. It's only a 440.
Or 5 over the hydraulic cam 396.
There you go. Right. So what we're looking at basically is that it threw away some bottom end torque with the Street Dominator intake, but we don't really care because it's a small amount, it's below torque converter stall speed, and it made enough extra horsepower that we're happy with it. Happy enough that we're gonna move on to Boost.
Ooh, that's gonna be even more extra horsepower, hopefully.
Let's turbo this turd.
Turbo time.
Oh boy, I can't wait.
So here is our implement of boost. This whole contraption was put together by Richard Holdner, who tests here for his own YouTube channel, so you may have seen this before. However, we're running it with a different turbo, different intake manifold, and different cylinder head swap than you saw in his program. So he cobbled this just for dyno use. It doesn't fit any car, but it's pretty clever because it starts with stock Dodge 440 truck exhaust manifolds. They're not flipped upside down or anything like that. The hot side comes out of both manifolds, wise into the turbocharger, which is a Borg-Warner S275. You can pick the eBay unit of your choice. It'll probably be similar, but we like the American-made unit there. On the cold side, this discharge right here feeds into a CSU carburetor hat, and we're also using a CSU carburetor, which is designed specifically for blow-through applications. We've used this a bunch out here at Westech, and it's pretty turnkey. How about all these hoses running everywhere? This is an oil feed line into the turbo. Had to punch a hole in the pan for the oil return line. Then, of course, you've got vacuum going down there to the wastegates, or I should say actually a manifold reference going to the wastegates, which are on the spring. We're gonna run about 7 PSI. We're not trying to kill this thing. That same manifold reference goes up there to the blow-off valve, and behind the hat, we have got our boost reference for the fuel system, which is also our boost pressure gauge. We've only got boost here in the hat, not in the manifold. So there you go. That and the O2 sensor to read air-fuel ratio to try and keep this thing alive. I don't want to blow it up, but I think we should make, I don't know, a couple hundred horsepower, 150? Let's see. doesn't make it smoke any less, that's for sure. So we made 9 pounds of boost. And actually 1 pound of boost is a significant correction there. And it probably is gonna disappoint a lot of people, I think.
You think so?
Am I downplaying too much?
Yeah.
Okay, here's the news. It made 644.5 pound-feet of torque, which is wow, and it made 514 horsepower, which is probably people going, what? I thought you had a turbo. But the junk is stock. It's, you know, it's blowing smoke. It's got a tiny camshaft. It's got no cylinder head. Let's look at the curve and then compare it to naturally aspirated so you can see that this is actually a win.
Wow.
Wow. Wow on the curve. Okay, to be clear, in case you cannot figure it out on your own, these red lines are naturally aspirated. These black lines are under boost. So look at everything that went on here. First of all, how much torque did it pick up? From 433 to 632. So that's 200 pound-feet of torque. 200. How much horsepower did it pick up?
148.
148, almost 150 horsepower. So I was sort of preparing the audience for the low 500 horsepower number. What's your take on that?
Well, it just won't run out the back door. I mean, you're RPM limited, so to get a lot of power, it takes a lot of boost and a lot of cylinder pressure, and we didn't want to blow it up. I mean, we're at 8 to 9 pounds of boost, and what if we were at 14 or 24? We'd have an engine blown up.
Yeah, you get to pick your power, and we don't want to do that.
Yeah.
Can you talk a little about ignition timing and what we did here versus the compression ratio?
As you compress or add cylinder pressure, the mixture ignites faster. And so you don't need as much ignition timing. But looking at something like this, the cylinder pressure really isn't any greater here than maybe with 12-to-1 compression.
Which you're judging on BMEP.
Yeah, break mean effective pressure, which it's a theoretical number, but it's some representation of what the cylinder pressure is averaged throughout the power cycle.
And more importantly, it's a made-up number, but in your head, you know, well, a 13-to-1 compression engine is going to do this.
It's a number I see all the time.
Right.
So
So
I look at
what is
12
the
to 1.
number here?
It was in the mid-180s.
Okay, so basically that's as if this was an, you know what? I bet you his 12.5 to 1 440 was right there.
It is.
Right. Yeah. Exactly. So basically what we just did is ran this thing at 12.5 to 1 compression by adding air into the cylinders, which makes for more pressure. And because we're starting at 7.2 to 1.
There'll probably be a lot of guys that poo-poo and say you can't do that, but it's got 36 degrees of timing in it.
36 degrees. Yeah. But it wanted 42 naturally
Yeah, so it's
aspirated.
back some. I mean, but the 42 was not big gains from 36 when we ran it earlier. It picked up 5 or 8 or something.
Well, and that's because it's such a steaming turd.
Pile.
Right? Anyway, I think if we had this turbo in a car, we'd be thrilled to death with 644 pound-feet of torque.
Yeah.
Let's go put some cylinder heads on it and see what the gains are, both naturally aspirated and under boost.
I think that might help quite a bit.
Hopefully.
Yeah.
The last couple times we've done motorhome 440s, a lot of people who are viewers have asked, you know, what would it do if it had aluminum heads on it, aftermarket heads? So that's what we're about to find out. I've chose this TrickFlow Specialties head, TFS. First of all, it is fully CNC ported. We picked the model with the 240cc inlet ports instead of the Maxwedge style 270s. And on the chambers, first of all, the intake valve size is 2.190 inches. The stock 440 valve is 2.08 inches. So it's a huge difference. So these are way too trick for what we're doing. I really hope they make a big difference. If they don't, I'm gonna blame that engine because it is a pooch. Is that distributor gonna clear this thing? There we go. That was kind of a lot, but we got our super trick cylinder heads on our super junk engine with our really nice roller rockers and everything, and I really hope it makes power. Guess that's it. All right, we got 3/4 of a point more compression. We lost weight, not that that matters on the dyno, and we got a way better flowing head. So we're gonna pull it now and hopefully it makes a ton more naturally aspirated power. Hit it, Steve. Our new power numbers for the 440 with the TFS aluminum heads are going to be 432.9 horsepower and 473.7 pound-feet of torque. Let's have a look at how it compares with those iron heads. Whoa!
Wow. That's huge.
That is a massive difference.
Pretty good head.
Yeah. I think the thing a lot of people might not realize, because you read so much about, you know, oh, a bigger head is going to kill low-end torque. No. The stock head is so bad that this thing just makes power everywhere.
Well, yeah, 440 is like having a small block Chevy head on a big block, so.
Yeah, by which he means the ports on the big block Chrysler are just way too small. They're like small block ports on a big block, as you can see by this. And even with a tiny, tiny camshaft, for it to make this much meat right here, that's absurd.
I'm going to show something else too. From where it made peak power before, the larger port, how much it carried. It changed where peak power occurs by about 400 or 500 RPM.
Yeah.
Yeah. And you can use that all the way down the track too. I mean, RPM is going to be ET.
The great thing about this is that's a massive difference in power with no cost to drivability at all.
No, none whatsoever.
Right.
Yeah, there's no downside to that swap. Yeah, that is a win for TFS right there.
Still want to put pistons and rings in it though.
Nah, turbo.
Turbo it.
Fix it.
Yeah, we'll remove the pistons for you. So, ready to go hang that on there?
I'll do it.
All right, let's go. Turbo. We're all dialed in with our aluminum heads with the turbocharger. We're gonna go see what this does. Fingers crossed for 600 horsepower and the short block staying together. Okay, go ahead, Steve. If it blows up, I hope he doesn't hurt my cylinder heads.
Oh, I know. I hope it doesn't blow up.
Me too.
Ooh.
Man, that thing's a smoker.
Wow. It just came just a tick under your 600 number you were hoping for.
I think it's good enough. Maybe we should let it live.
Oh, no. Boost her up, baby.
Look at that thing. So I don't know if you were looking at gauges or what, but we saw a lot of smoke out of both the exhaust and the breather.
I couldn't watch the engine because I was doing this.
So first, can we look at the boost curves? See how similar we were to with the stock heads? So the blue line here is our boost with the iron heads, and red is with the aluminum heads. It's kind of the same. Our scale here is only 8.7 up to 9.2. So even though it looks like a radical change, it kind of isn't. All right, let's get to the meat of it though. The power. What did it make? And it made 652 pound-feet of torque and 592 horsepower. Missed my 600 guess by that much. This is the thing that we see all of the time. Whatever gain you make naturally aspirated is the gain that you see under boost. And there you go. With the same boost, the same engine, two different cylinder heads, the NA gain was about 75 horsepower and the boosted gain was about 75 horsepower.
Like they say, build the best NA engine you can because that's going to be the best boosted engine you can build.
Yep, I think that demonstrates that once again. What do you think, Dolchek?
I think, are you guys going to address the elephant in the room here?
Oh, no.
I mean, seriously, we're at 592 horsepower. If you had 8 more,
even Brule wants to fix it.
Yeah.
Have you ever seen Steve want to turn up the boost before, ever?
He doesn't care about this motor because he thinks it's a turkey. But
when Troy was in the cell helping us earlier, I told him to move away from the side of the engine. Just make sure nothing hit him.
All right, I want to see your best impersonation of a millennial. Go in there and turn the knob.
I can do it.
All right, Dulcich, this is it. I'm calling it after this.
Really?
How come I'm the one with like cold feet and Brule is the one to be like, hey, crank it up?
I know, it's like a role reversal
It
deal.
is.
But the thing is, I don't know if this can make more than 600 horsepower or even make 600.
Yeah. Piston rings are done.
Yeah.
They're over.
She's had it, man.
Not happening. Yeah, but literally the piston rings will not handle more boost. We keep cranking up the boost and the power keeps dropping. It's just blow by.
That thing's had it, guys.
We have fun, though. Did you see the torque number on that last
I
poll?
did.
Let's
I
have
did.
a look at it. 694.3 pound-feet of torque. And this is all at like, 3,600 RPM or something like that. Up top, it only made 589. Literally, we keep cranking boost into it. That number keeps dropping up there. This thing is happy at basically 9 pounds, making 590 horsepower and 650 pound-feet. That's the comfort zone of our turd of a 440.
Like Brule was saying, a set of rings, and maybe that gets a whole lot better.
By the time I've got the bottom end apart for a set of rings,
Yeah.
I'm putting it together the right way.
That makes sense.
That's kind of the point. I mean, we learned a lot here. So now with a fresh engine, then you kind of know where you're at already.
Yeah.
So
We did see that turbos definitely make power.
Well, and we also saw, once again, that NA power gains with the cylinder heads add right up to turbo power gains with the cylinder heads. At the same boost level, it makes the same increase. Cool.
Yeah.
Ready to wrap it up?
I am.
We can talk about you behind your back. That's what's going to happen right now. All right.
What's new?
What's new? I only have two things for you.
I'm ready for them.
One of them, I'm not going to even believe your answer because I know that you're just going to go straight to the faith in Ma Mopar. What is the longevity of this short block?
Oh, take that much boost all day long. Are you kidding? Look, this thing's pretty worn out, and we hammered it with 9 or 10 pounds of boost, and it's no worse.
You really believe that the main caps and the rods are going to take that over and over and over and over?
The internet says the turbos are a lot easier on the bottom end at any given horsepower level, and I believe it.
But at main caps, I mean, why do they make girdles and everything for the Mopars if they can actually just hang?
Just for extra peace of mind and sell parts. All right?
Okay, well, I'll give you this. We know that 440s survive at 600 horsepower and beyond all day long. I don't know about the 700 pound-feet of torque down at lower RPM. That's my concern.
I got to give you that one.
Yeah.
I'm not 100% comfortable there either.
So I guess question one, undecided, but we could find out. Question two, should we reveal to the audience what we hope to do with this monstrosity?
Oh, I would not want to leave them hanging.
Our hope is that we will be able to take this very motorhome 440 and throw it in a car on Roadkill Garage. Will it happen? Well, that's question number 3, and we'll never really know, but that's our scheme. We will see you next time on
Engine Masters. Did you know that I saw these on highway patrol cars in the Central Valley back in the day when they had the 440 Monacos?
Yeah, compared to the 429 LTDs, they needed all the help they could get.
I disagree. I think that the 440 Dodge Monaco of 1977 and 78 were the finest police vehicles ever.
Not compared to the Cobra Jet 460s, right? Or
They had a 429.
Or police
LTD.
interceptor.
Yeah, and they were awesome.
Welcome to the Dyno! We've got fun and games, and we're gonna take you behind the scenes in how we handle our hunt for horsepower. This is going to be a very special episode of Engine Masters. Kind of like the Brady Bunch Goes to Hawaii, but a different kind of vacation. Because I'm going to do my best to put you in our shoes to see what it's like to go behind the scenes for a day at the dyno here at West Tech Performance Group in Mira Loma, California. What we're going to do is show you how you would show up with your engine prepared, why you would want to come to the dyno with your engine to begin with, how you hang it on the dyno. We're going to show you how the dyno works, look at how we break in an engine, how we tune it up, and of course, how to judge whether the engine is any good or not. All of that this time on Engine Masters. Now, let me tell you about this lovely engine that is going to be the victim of this episode. This is the COVID 350. You've probably seen it on my social media. You may have even seen it on an episode of Roadkill where we did sort of a working from home deal with me and Finnegan, and I assembled this out of parts that were literally left over in my garage, which I know looks really greedy, but this represents 30 years of hoarding parts. Let me tell you what it's all about. First of all, it's a 355 cubic inch small block Chevy, very standard stuff. It's just got a stock cast crank, H-beam rods, forged pistons. It is 11 1/4 to 1 compression, which makes it pretty good. And it allowed me to do things like install a big solid roller cam. It's a Comp Cam's off-the-shelf unit. The duration at 50 is 242, 248. I've got rocker arms on it with a 1.65 to 1 ratio for 600 lift, which makes it good because you can walk around going, I got 600 lift. Now, the cylinder heads you should recognize because they've been on that 383 small block that you've seen on a cajillion episodes of Engine Masters. They're the Blueprint Engines 210cc CNC ported heads. Up top, Holley 850 double pumper that just really stabbed my hand on that vent. That really hurt. And I've got an Edelbrock Super Victor intake manifold on it, MSD ignition. We've already got the Dyno headers on this thing, and it is mounted to the Dyno cart. And we've got the special flywheel installed, which I will show you once we get inside the room and take you behind the scenes on this Dyno Test. Let me get this thing out of here. One of the things you got to pay attention to is not knocking the engine off the cart, because right now it's not actually attached at the back. So first of all, why would you even want to dyno test your engine? Well, first of all, because it's really fun. I guess one of the big deals for me is if you have a brand new engine like this, you can break in your cam. If you've got a flat tappet cam, that's huge. But you can also make sure nothing's gonna break before you put it in the car. Leak checking is a really big thing. And of course, you can get a baseline tune-up for both your ignition timing and your carburetor or EFI. And of course, you get to walk away with the horsepower number and brag to all your friends that you have dyno proven power. When you bring your engine in, you want it to be as complete as possible. Once you get your engine here at the shop, it'll get mounted onto a rolling cart like this, which is super handy. You want to have motor mount brackets on it to hang it on there. And they'll install a flywheel that matches the balance to your engine. So if the dyno shop you're dealing with doesn't have that, if you've got, I don't know, a Ford FE or something that they're not commonly dyno testing, you want to make sure you've got that. They'll bolt on this drive plate that has a hub in it, like a clutch with springs, that's going to mount here to this spud that attaches to the dyno. And of course, there's a regular old bell housing, like a manual transmission bell housing, that's also used to couple it to the dyno. In our case here, you don't have to run a starter on the engine. There are twin starters under here that attach to the dyno itself, so we don't have to deal with matching that all up to a flex plate and wiring that every single time. But some dynos actually, you have to have a starter with them. I don't have a lot of experience with other types of dynos other than this, but there are some that do not require a bell housing or a flywheel, and they have more of sort of a drive shaft situation and different methods of mounting the engine to the cart. So you can ask those questions before you go to the dyno shop. So they've pre-leveled the thing, because one of the deals is it's got to go in this way, but it's also got to be leveled up and down, and it can't be like this. We used to fight with this a whole lot more. And Brulé is the only guy who sticks his arm in the bell housing and has the trust that nobody's gonna wiggle the engine and pinch his finger off.
As David was explaining kind of the rear of the drive system, the flywheel and all that, we've now slid it onto the input shaft, which is just not dissimilar to like an old Muncie 1 3/8 10 spline. What we have here is a water brake or an absorber, which basically is for lack of a better term, it's a variable speed torque converter. It's controlled with a servo on the bottom, which either holds or releases water to maintain engine RPM and load. What we're doing is measuring torque with what's called a strain gauge or a load cell, and basically what it is kind of an electronic rubber band which changes in millivolts. So it's actually calibrated, and then we actually measure torque. And between torque and RPM, we calculate horsepower. So there are observed channels and measured channels. Basically, this is the brain of the thing back here, this control box. We're monitoring fuel pressure and oil pressure, all of those things. But the meat of any engine dyno is really measuring torque, engine speed, which calculates to horsepower. All the other stuff is kind of things to look at the health of the engine or the potential of the engine.
So he's hooking up the oil pressure, I'm hooking up the fuel lines. You can see that we have both an A and a B fuel line here, and you'll often see Steve looking at the fuel flow on each bowl to sort of judge what's happening with the jetting in each end. So all of the water stuff that we deal with all the time, I never know what valves you're opening and closing and what the huge tank does outside and the heat exchanger and all that stuff.
Well, as far as the stuff I'm adjusting on the capacity valve and that sort of thing, it's really to kind of contour the absorber to the power output of the engine, because that electronic servo only has a certain amount of sweep. And so I'm basically increasing...
The servo being the dump, basically?
Yeah, the dump, the electronic dump that's controlled by the computer.
The releasing the water out of the torque converter, so to speak.
So what I'm doing with that capacity valve back there is kind of contouring the ability of the absorber for more or less torque, which is more or less water, because we want to keep that servo in a sweeping range for the RPM range we're running it. And so I basically reduce the water or increase the water for engine torque.
This is actually the Westech Super Custom Stainless Steel handmade water tank. It's got a radiator cap that goes here up on the top. And then this is a water-to-water heat exchanger. So there's tubes that run inside the thing and water that goes around the outside of it. And so you got cool water from the giant tank, and then you've got water out of the engine. And it works like a water-to-water or an air-to-water intercooler, basically, except for it's water-to-water.
This is one of the fuel turbines. Basically what it is, it's a little paddle wheel inside of this housing, and it has an optical pickup. So as that paddle wheel spins, it's actually counting. And so as the fuel passes through and goes up to the B turbine, we're able to count the fuel in pounds per hour and actually ultimately calculate that into gallons if we want to. What we're able to do is we have an A turbine and a B turbine, which allows us to read the primary and secondary bowl of a single 4-barrel carburetor, or primaries and secondaries in, let's say, a tunnel ram carburetor. What that allows us to do is make sure that we're not rich on the front, lean on the back, or left and right with a tunnel ram, those sorts of things. It's just another piece of the equation for data that we can look at to help us tune.
Steve showed you about the fuel flow and how that's measured. Also, fuel pressure is internal to the dyno. Some of the instrumentation that we do that involves the engine, well, this is dyno. We deal with water temperature here. That's what this is reading. We've got oil pressure hooked up just like you normally would with your odometer gauge on your dash. It just connects to the dyno. We also have a wideband oxygen sensor here. Sometimes we'll run 8 of them in every single header tube, so we can look at the air-fuel ratio cylinder to cylinder. On a standard deal like this, we'll just put 1 of them in a collector. It's obviously about 18 inches back from the opening, so it doesn't get oxygen contaminated. And speaking of contamination, the other thing is if we have a brand new engine that's never run before, especially if it's a customer that Steve doesn't trust, like, you know, Dulcich or somebody like that, we'll not put the oxygen sensor in for initial fire up, just so that it doesn't get wet with water, oil, overly rich mixture, any kind of disaster. This is run before, and it's already broken in. So we will start with this all hooked up. I can never find the plugs once they're thrown over. That's why we need Troy. Watch this. Hey, Troy. See? Pork chop's good that way.
One of the other pieces of equipment that we frequently use, and we have actually in past episodes when we're trying to kind of figure out why an engine makes more or less horsepower and we're looking at airflow. Basically what this is, it's a little generator and it measures airflow down through the carburetor. And then again, it's calibrated to the electronics on the dyno, but it's got this aluminum honeycomb, a little fan there, and it actually, as air is moving through the carburetor, it spins the little fan. And again, it's calculated. We don't hardly ever, well, we did once, use this when we were running nitrous, and we don't any longer because this is really very fragile honeycomb to kind of direct the air and make sure that it's straight and the fan operates properly. But any sort of backfire or anything can damage this thing really easily. So this is really more like development sort of stuff, not necessarily having to run it on every engine every day.
Okay, Steve, before we fire this thing up, what are the most common questions that you get from new customers or people who show up here for the first time?
I'll get emails that say, how much does it cost to dyno my engine? A little more information, please.
Okay.
You know, a lot of times things will come over the internet and it's very vague, and there's a lot more to it than that. I mean, I really want to talk to someone on the phone. I want to ask them about water pump and configuration and pulleys and whether it's EFI or carbureted.
Blown turbo, some crazy contraption with 2 blowers and 3 turbos.
E85 or gasoline, all the way down to the point of, If you're bringing your headers, have they recently been coated?
Right.
Or are they seasoned? Because does it have a flat tappet? Does it have a roller? I mean, all of those things play one part to the other, so.
So on the header coating, if you break in the engine with a fresh set of coated headers, it bakes it off, right?
Now it's a bubbled coated header.
It completely ruins it. That's something I wouldn't have ever even considered for this,
Yeah, you have to season them, and you can't season them with a flat tappet very well, so. We'll use our headers first, break the camshaft in, then put their headers on after the camshaft's broke in to season their header, and then run it with their headers.
Do you recall ever getting this kind of care?
Oh, all the time. I'm kind of curious, have you ever had someone come in so underprepared that you had to send them home, or?
It's worse than he ever has been.
I mean, the worst one I remember is I had a short block. Outside, when you came in, I was sitting on the curb porting the heads, and you had to get the thing tested that day.
Okay, so you want to walk us through what you would be doing for an initial break-in thing? You want to go start it and show what Troy's going to work on, and et cetera?
Sure, absolutely.
Walk us through as if we're ignorant, because, as you know,
well,
we're not.
Troy's out in the cell, which he normally is on startup, and we're going to check for any sort of fuel leaks initially. We're going to crank it for oil pressure before we start it. We're just going to check some real basic stuff. And then upon startup, he's going to do a walk around and inspection. He's got a heat gun in his hand, so he can go ahead and check and make sure we've got temperature in all 8 cylinders. He'll take a listen to the valve train, and then he'll go ahead and check timing for me. And we kind of have, we've been doing this long enough together, we've kind of got a hand signal program worked out, so we really don't have to talk to each other much.
Brule, being old that he is, he's hard at hearing, so we have to use hand signals. So what's going to happen is when Steve is in there and getting ready to fire it up, I will be ready with the temp gun and check the temperature of each cylinder and make sure they're all firing right.
This engine happens to have a solid roller camshaft, so my typical procedure would be to just start it up, make sure that we have base timing set. I'm going to warm it up to kind of test temperature, and then we're going to shut it off, and I'm going to go out and relash the valves after initial startup, just so I'm comfortable with that. Once we come back in, I'll run it through a break-in cycle, and then we'll start along our test procedure. So I can show you what some of that stuff looks like. And all we're doing right now is just letting it get up to some sort of reasonable operating temperature. It doesn't have to be 160 or 80. If it were a circle track engine, we would run it much warmer. This happens to be kind of a street and drag race engine, so we're going to actually run it in the 130-ish range. And so this is at about the point in time where I would just shut it off and go out and relash the valves just to make sure that we've got some temperature in it. They're all adjusted accurately. Okay, so we've got the valves lashed, and now I've come back into the console. One of the things that I think is interesting, it's a story I like to tell, is, you know, people say, well, why do I want to break it in, or how does that work by cycling the engine up and down and varying the RPM range? In the old days, somebody would tell you that you wanted to break it in by just going on a drive where it was kind of up and down hills and varying the throttle position. But I had an opportunity to look at a big block Chevrolet that someone had forgot to put an oil ring spacer in. It was a Stroker 496. And during the break-in cycle, I could see the engine smoke out of the passenger side header. And as the RPM increased, the smoke would go away. It would get to a little higher level, and it would smoke out the driver's side. So I was actually able to kind of visually see externally how the oil kind of fanned through the engine. So the whole idea was to keep the camshaft lubricated, to keep oil on the cylinder walls while they're seating, and to keep everything lubricated. So it was just kind of fun to be able to see what's actually happening inside the engine during the break-in process. So we'll go ahead and get it started up and run it through a break-in. Just gently bump it up to 3,100, and it's going to cycle it from 31 down to 27, back up to 31. We've run this engine before with a different carburetor. In the interim, we've changed carburetors because David's actually going to put this in a car, and this is the carburetor he'd like to run. even just trying to bring it up to an RPM and load to break it in, the air-fuel ratio is so lean we can't continue. And that's part of why you take things in small steps. We're gonna have to go out and address the carburetor issue a bit and upjet the primary circuit on the carburetor just to get the thing to cruise smoothly and to be able to run through the break-in process. This has a 72 jet in it. Typically I see 80 to 82 jets in these. I'm putting a 79 in it just to give it some fuel, and we'll I'm sure probably have to readjust some from there, but we just got to be able to make it run and not be so lean that it stumbles and runs hot.
Another thing that can make it lean like that is a really radical vacuum leak, which, by the way, on the dyno doesn't seem to matter at wide open throttle at all, but it'll affect like the drivability and the idle and stuff like that. So as soon as we ran out here, I started to look and see if the carburetor was missing any plugs. The one in the back was cracked, so is this one in the front. So that wasn't the problem, the jetting was the problem, but nonetheless, that's the type of thing that you can find out before you get the engine in the car.
Well, we got one full pull under our belt now. We ran it from 35 to 6,500. I can tell you that the engine's healthy. It's got a couple of little tune-up things that I think can be improved on, but before I go any further, since this thing belongs to David, and I always like Steve's opinion, I think I'm gonna go out there and talk it over with those guys.
The best part of this is I think Dulcich is really gonna like it.
I do like it already from what I've seen.
Oh,
Yeah.
you've been watching the data?
Oh, you bet I have.
I knew you'd appreciate it.
Yeah.
Let's have a look and see where we need to go. Really, the power is still on a little bit of a climb. We stopped at 6,500 RPM, and right there we're making 502.9 horsepower. So obviously that crests that 500 goal and only gets better from here. As far as torque, and we are looking at corrected numbers here, which Steve will explain in a minute, 442.7 at 4,800 RPM. So our spread, and we often look at this, the spread between the RPM at peak torque and the RPM at peak horsepower is 4,800 all the way up to 6,500. So that's an 1,800 RPM spread, which is good.
Yeah, it's really good.
Yeah.
What we typically see in LS stuff that's good.
Yeah. No, we really like to see that because it basically means the package is working.
Yeah.
It's not very what we would call peaky. Like if you saw the spread from 5,800 to 6,500, that's an engine that's only operating in that range, whereas this thing's fairly happy throughout the entire curve.
Yeah, it's a beautiful curve.
Yeah.
This is kind of almost an ideal situation when I look at an initial break-in and some testing. It's a little bit rich, not horrible.
So you say it's a little bit rich. We're looking at air-fuel ratio, which is the mixture of air and fuel as measured by the oxygen sensor in that tailpipe that I showed you, or in that header collector. And it starts out at 11.5 to 1 and ends up at about 12 to 1. We would call that rich because we're gonna target this thing later at 12.5 to 1 to 12.7 to 1.
What I generally do is on a normally aspirated engine is my target is horsepower. Wherever it makes the best power is the right air-fuel ratio. And I will sometimes see that at 12.2, and I'll sometimes see it at 12.8.
Okay, fair
So
point.
we're just gonna let the engine tell us what it wants.
Let me ask you this. When we start doing our timing sweeps, do you ever see timing affect the air-fuel ratio?
Slightly, not nearly as much as people think. I mean, they think as soon as you add timing, it's gonna get a whole bunch leaner. We might see it move a tenth or two, but I'm not gonna see big swings in air-fuel ratio.
Okay.
The other thing I like here is the oil pressure. It's got a really nice curve all the way up. And we were looking at that as we kept moving up in RPM, making sure all of those things were right.
So as far as the fuel mixture, we talked about air-fuel ratio. The other thing Steve looks at for drivability and just sort of the overall happiness of the carburetor is fuel flow in pounds per hour into the front and rear bowls individually. What do you see in there?
Well, what can happen is the air-fuel ratio can look like it's in a good range, but the front of the engine could be extra lean and the back of the engine extra rich, but it averages out to appear to be okay. So with this, I'm verifying that it has equal fuel flow in the front and rear. In a perfect situation, you would have good drivability, good wide open throttle, and at wide open those would be well balanced. That's a perfect situation. We get close. This thing looks really encouraging here. We're only a couple of pounds off. And we know it's rich, and we know it's rich at cruise, so we're going to be able to lean the whole carburetor out a little bit.
So tell me what we're going to do next.
2 and 2.
2 and 2. Yeah, back at Chuck Willery. I remember that. I'm thinking we take 3 and 3 out. You know, just something to get us closer. On this size carburetor, generally 4 jets out of the front and the rear will knock about a ratio out of it. So I don't want to get too greedy right away. Well, 2 is fine, 2 or 4. Get it into a range where I think the timing will actually make some effect, and then make that 1 jet change, then we'll do a timing change, then go back and finish it off with jet again. Yeah. And I think you got a package.
Okay, watch this. Have you noticed Dulcich hasn't had much camera time in this episode yet?
I know.
Yeah, so he should probably go change those jets.
Oh, wow, you're just putting me to work.
I know. I always find a way.
He's so benevolent. Well, as it turns out, the air-fuel ratio numbers appear to look like they're in a better spot, but it actually lost about 4 or 5 horsepower. So, like we had talked about earlier, is we kind of just let the engine tell us what it wants, and sometimes they want to be richer. So we're going to go back to the jetting, so it's very similar to what it was, richen it up just a little bit, and then go ahead and chase the timing.
The carb's fully dialed in now, and the next step is going to be taking a look at the timing. We had a base setting very conservatively at 32 degrees, so we're going to bump that up to 34 and then test it again and see if it picks up any power. If it picks up a lot, we may even go further to 36 until it stops giving us an improvement. So I'll just give the distributor a little twist, and then I'll give it a check with the timing light.
Now we're ready to look at some data. To review, we ended up first dialing in our fuel curve and then going to the ignition timing. So let's look at what we learned there.
So this is actually after changing the primary jet because it wouldn't even run to break it in.
Right, fair point.
So we added some fuel there. So we were a little closer than it may have been, but we couldn't run it the way it was. And so that's what we had there.
Okay, so let's compare that with what we ended up with our fuel curve. And I will say our jet changes on this thing were, after that initial step where it was way too lean, we were talking tiny. We never change 1 jet number at a time in a Holly, like for example, from 72 to 73, but we did that today, which was kind of dumb, but it worked.
Okay.
There you go. Big difference just from a couple of jet numbers right there. So that's one of the reasons why you want to come to the dyno. You've now got a baseline. I have found that when you take the engine off the dyno and put it in a car, you don't necessarily get the same results. It's not going to track the same air-fuel ratio numbers because of underhood heat, what you've got for an air cleaner,
exhaust,
scoop, exhaust. Yeah, when you put an exhaust system on it, it tends to like richen it up, all those things. But it gives you a point to start from.
Yeah, and it depends on the application too. I mean, when we do some of the drag boat stuff, it comes off the dyno, goes in, and never gets touched, and they're pretty much spot on. But again, they have the same fresh air, open headers. Right. It's a much more similar situation. Mm-hmm. So anytime you change other components, mufflers, exhaust system under the hood temp, air filters, air cleaners, that type of thing, it's going to change some of the results.
So now let's just look at our best curve after we adjusted the fuel and compare that with the timing that we were messing around with. And we did end up changing the timing from an observed 30 degrees to 32 to 35 and even 36. And it was really insensitive above 32 degrees. At 30 degrees, man, it threw away power. I've never seen 2 degrees make that kind of a change. As a matter of fact, I think because Troy initially set it up and then you were looking at it, I think it was a different parallax on the light and comparing the mark in a different place.
I suspect that we probably were looking at it a little differently because I got it right and Troy did his best. Right?
Well, that's one reason why often we have a rule here. If it's your engine, you set the timing so that you can repeat it in the car. We didn't do that this time.
Yeah.
Although, you know, my crew chief here probably will be dealing with that engine if it ever gets in the car, so we're good. But anyway, we found the optimal timing for it, which is an indicated 34.
Right.
Okay, and how did that look? Not a whole lot different. As a matter of fact, it's down just a little bit right here, just from variance from test to test. But
Freiberger, I have to confess, I honestly think that's the difference between 34 and 35 degrees.
Yeah,
so 1 degree difference. And
Yeah.
it's virtually an overlay. That's within dyno variation, if you ask me.
Which is really another point, I think. If you go to a dyno shop and they run the thing a few times and they can't overlay a curve like this, there's a problem going on. That's one of the things that makes Steve great, is he's like paying attention to not just the coolant temperature, but in his head, he's also thinking about the combustion chamber temperature, because you can have the same coolant temperature whether you just rushed a bunch of water into the engine and the chambers are still hot, or whether the thing's actually settled. And his dyno brain has got that sort of dialed in.
Well, it just kind of turns into muscle memory after this long, but you've seen me do it. Let the engine idle for a while so the combustion chamber temperature drops. Even though the water temperature still reads the same, the combustion chamber temperature is lower, and it'll make more power.
Yeah.
So you can play little games like that, and we try really hard not to, because we want every test to be a comparison. We don't want to just have random numbers. I love the engine dyno because it's so much easier to do that with the equipment we have than it is on a chassis dyno when you have even more variations.
And finally, the punchline we all want to know when we go to the dyno, which is what is our peak power numbers? And the COVID 350 barely breaks into that 500 that everyone wants to see. It's 501.9 horsepower at 6,500 RPM. And by the way, in previous tests, we ran this thing all the way out to 7, and it carries very nicely. And once again, the spread between peak torque and peak horsepower is huge. At 4,700 RPM, we made 447.7 pound-feet of torque. So now, you may heap the praise. Now, I understand these days 500 horsepower is no big deal, but what we do to look at an engine and decide if it's good or bad is more than just the peak power number, because a 500 horsepower 540 big block Chevy is worthless. A 500 horsepower 355 Chevy on pump gas is pretty good. So let's talk about how we decide that.
Well, I mean, for me, the number to look at is always specific torque. And that's because the torque that you produce per cubic inch just falls in a narrow range, and you can judge if you're on the upper end of that range, man, you're doing pretty good. If you're on the lower end, then not so much. So where are you at, Freiberger?
So what he's talking about is pound-feet of torque per cubic inch, specific output. It is 1.26 on this engine.
Okay, that's a very respectable number for a pump gas engine, for sure. Wouldn't you think, Brule?
No, absolutely. Kind of the number I use in my head a lot, and because I have seen a lot of engines kind of end up there that were good. And on an average, I would say some of the best pump gas stuff that's a true street engine, you know, 10 1/4, 10 1/2 to 1 with a really good cylinder head and a hydraulic roller camshaft, they end up, I mean, kind of a target for me is 1.25.
Okay.
Yeah.
I see a lot of iron-headed stuff down at 1.15, some pretty decent stuff, 1.2. So at 1.26, that's a really good number for pump gas.
The specific horsepower output, horsepower per cubic inch, is 1.4, 1.41. Also pretty good for something like this.
Absolutely.
All right, well, that was a lot of really technical gobbledygook, but I hope you realize on every episode how much fun we have going through it and sort of nitpicking it and discovering why power is great and what engines are good and what engines are bad. And on that note, I'm not satisfied yet with you guys having told me that this is a great engine. I'd like a little bit more.
Okay.
You can just sort of feed it in. No, it's not
Very
that
good.
awesome, but it actually came out pretty good. It's a fairly good street 355.
There's no question it turned out really well.
I can remember being in high school or my earlier years, you didn't go to the dyno, you know, you couldn't afford it at the time. There weren't that many dynos around, as a matter of fact, but if you're an engine geek and you want to improve your game, the dyno is where you do it, because you have all this data. You could get all that feedback. Oh, is that working? Is that making it better or worse? You get dyno brain Brule and your buddies there. And, you know, like the dyno is probably one of my favorite things. So.
Well, it is me too. You just made it sound so fun.
Oh,
All we
it is.
really need is beer. Can we work that out next time?
There's some in the fridge right
Oh, that'd
now.
be fantastic.
I'm
All
on my
right,
way.
we're out for that. Thanks for watching. We'll see you next time on Engine Masters. Up top, Holley 850 double pumper that just really stabbed my hand hard on that vent. That really hurt. Look,
That's sharp.
yeah.
Pointy.
It needs mechanical 8-stack.
Who's speaking here? If I were to call him and go, hey, Brule, on Engine Masters, I want to run stack EFI on this thing.
On a
he
pill.
would immediately be like rubbing his head.
Well, here's my thing.
What's
okay?
our schedule? That's
What's
what
our
I'd say.
schedule? This time on Engine Masters, the power of Lobe versus high-performance ignition. I know you think you're watching the wrong show, because yes, that is a big block Ford, the very first 385 series engine to appear on Engine Masters, because so many people have been asking for it. This is in fact about a 20-year-old Ford Motorsport crate engine. It's a 514. These things in a stock block will take huge strokes, like 557 cubic inches. They're really great. This crate engine has the Super Cobra Jet heads, and the only deviation from stock on this thing is the Comp Cam solid roller camshaft. It's an XE286R, and it does have an Edelbrock Victor intake manifold. So this thing is stout. It's good for like 650 pound-feet, 625 horsepower, something like that. And this is another thing that the audience has demanded over and over and over, and that I've resisted. It is a test of ignitions. Here's how it's gonna work. First of all, I have loaded this thing right now with the worst possible ignition system I could devise. It's got a cheapy parts store single point distributor in it. The spark plug wires are a combination of stuff from Dulcich's backyard and from Brule's old 327. They're like original GM wires. And we're gonna run it with a clapped out old coil to begin with, the worst that you can get. And then we're sort of gonna let the engine tell us where we progress from there. Ultimately, we plan to end up with full electronic ignition and an MSD box and a great coil, everything that you asked for. So we're gonna roll it into the dyno now and see how badly it misfires with all of this junk on it, and then slowly keep throwing better and better parts at it to see if it makes a difference at all.
So probably only the old guys are going to remember this. This is a tachometer, volt-ohm dwell meter. I think I bought this in 1971 or 2. It was actually in an era where I got the original instructions, and there's actually a supplement to this for electronic ignitions. They were so new then, but we have a chance to use it on this. So we're going to check the dwell. Should be 28 to 32. Steve's going to crank it. We can see it right here.
So the dwell's basically telling you how long the points are closed.
Yes, and how long the coil has a chance to recharge, and then when the points open up, then it discharges the coil.
Yeah, and it's a measurement of degrees. Okay, you want me to hit it?
Yeah. Yeah, so on the 8-cylinder scale, dwell time on a V8 should be 28 to 32 degrees of dwell, and this is right at 30, so we're spot on the money.
You said you bought that in 1971?
Man, in the early 70s.
So you were like 3?
I wish.
So did you write down that dwell number with your quill and parchment, or do you just go ahead and chisel it right into the rock?
Lasts longer with the rock.
Right. All right, this is gonna be one of those episodes I have to apologize to you guys for.
Why?
I didn't want to do it. Did you? No. Did you?
Yeah.
No, but the audience forced it. They kept on asking, I want to see ignition make power. And so to do that, I had to back this thing up all the way to the point where I hope that it just falls on its face.
There's a good chance. I mean, with the stuff that we've got on there now.
Those plugs are wasted. The wires are junk. It's a leftover coil from the vineyard. Yeah.
It's out of my 67 Bonneville. I think it might be original.
Okay, so we're gonna fire up this 514 cubic inch Ford, big block Ford, finally. And I think we're gonna have a misfire problem.
We might.
We just might.
Junk.
All right.
Did you see that?
That's the worst.
I've never seen that.
I don't know if we're gonna be able to run it at all. That was the worst thing I've ever seen on Engine Masters, and you know,
I had to take a rollback out of that one and give it a nice slow check again because I've never seen one shake like that on the dyno.
Well, and explain that. Why was it that big of a disaster on load-in, but then you actually were able to give it load and sweep up to a point where it fell apart again?
Well, I think I let whatever was misfiring, the bad spark plug or whatever was in there, kind of catch up and start firing and roll in slowly. When I gave it, accelerated pretty quickly. I think the additional fuel caused it to misfire, and then it just went to,
oh, right.
You know, so I had to stop. I'll throw more boost at your junk, but I'm not throwing ours up like that.
So what just happened there is the worst misfire in the history of the show. And so let's look at just how bad the power curve is when you do something like that. Wow. It's amazing it still made 646.9 pound-feet of torque and 621 horsepower, but it's a disaster. Look how once it starts to misfire up the top end, it's just all over.
And look at all this. I mean, it took that long to kind of get firing again, I think.
But then once it ran, look at the tabletop torque curve.
Yeah, I mean, that's a lot of power at 5,000 RPM for something that's on the verge of misfiring, and well, it is in this area.
That's a disaster.
I would say the ignition system right now is barely adequate.
I would say that too.
Right?
The question is,
barely functioning.
We know that we've preloaded it with doo-doo. What do we change first?
Those spark plug wires are collector items off of 62, 283.
The collector's items, huh?
Date code correct, right?
Yeah, they are. So is that your vote?
That's my vote, is plug wires.
Okay, I got an $18 set of the worst possible plug wires I could buy at Pep Boys. So you want to install that?
Yeah, sure.
Yeah.
Okay, first up, brand new cheapy spark plug wires. These are my $18 spark plug wires that I purchased at Pep Boys only yesterday. So these are not like Trick high performance wires. These are what we used to call rag core when I worked at Jacobs Electronics. They are not a spiral metal core. They have like a carbon impregnated, I don't know, fabric in them. And they don't last that long and they're super cheap, but I have a feeling they're gonna solve quite a bit of our misfire problem. I'll put them there, go get my mask, and by the time I come back, hopefully those guys will have installed them. Want me to just go get you guys a beer or something?
My side's all done. We're ready.
Wrap that up. We're about to look at the data. Basically, the first time we ran it, it was a disaster. We put spark plug wires on it. We improved a lot of low-end power, but we're having trouble keeping the coolant temperature consistent because of the mechanical water pump, so we're gonna have to run it hotter than normal. So we've now re-baselined it at the hotter temperature. This will be the baseline that we will judge the rest of the tests in the episode from. Let's look how different it is, actually. Yeah, that's the difference between hot water temperature and cold water temperature. Obviously, cooler is the red line, making more power. Hotter is the black line, making less power. The black line's our new baseline. You can see that we solved the low-end misfire problem. We're still having a disaster up at the top end. Let me give you our new baseline power numbers. So what's really interesting now is that our torque peak is 635.1 pound-feet. The curve is just so flat that it's all the way out there at like 48 or 4,900 RPM, really high, and very close to the horsepower peak of 611.7 horsepower, which is happening right at the point where the thing falls apart and is having a big misfire problem. So the power points here, like the RPM at the peak, is sort of misleading information because of the misfire problem and because of the shape of this super flat torque curve.
Yeah, we would typically expect to see peak power happen 1,000, 1,200, 1,300 RPM after peak torque, and that's not happening. It's only about 300 right now, so we have a chance when we fix that up.
I feel obligated as our next fix to do spark plugs because we know they're so fouled.
Yeah, they're fouled.
I know you don't think it's spark plugs creating the problem, and I'll buy that, but I feel...
You can read my mind,
we're
Freiberger.
morally obligated to change the spark plugs.
We want to have good parts in here so, you know, we can rule that out of it completely and then see if upgraded components are going to help this thing with the ignition.
All right, let me grab some new plugs. Basically, these days on something like this, I'll look at the plug, and if a gap is there, it's fine. If you have a turbo or a heavy boost deal these days, you definitely want to close the stuff down to like, 22, 25, sometimes less. Okay. Oh, these wires don't like to clip on. There you go. All right, we changed our plugs. They weren't as dirty as I hoped. They cleaned up in that engine, but now we have a brand new set of cheap, made in China, Autolite spark plugs in there.
That's gonna be big power, bro.
Let's go.
There's that little smirk, Brule.
From one run to the next, and nothing else changed but the plugs. So
Even though at the top end, we think it's point float, right? Maybe the point spring is getting worse.
from one run to the next.
Okay, I don't know. So the red line is actually our test with the old dirty spark plugs, and the black line is with our new Autolites. And it's a little bit down overall.
But keep in mind, our old dirty plugs were not
NGKs,
really,
yeah.
they were a higher quality plug, and after we ran the engine a few times, they cleaned up. So they really weren't old and dirty anymore by the time we established this baseline.
Yeah, it's a little up here, down there, the same there, down there. And this is when we actually could hear the misfire was worse.
Yeah.
Is in this area. And like you say, it could be that we're dealing with points, the points getting weaker as we go, or spark plug.
Or coil.
Should we change the coil before we mess with the points?
Sure.
Yeah, okay. I guess we might as well.
That was
right?
like a standoff to see who would get up and go change the coil, right?
That's what that was.
Well, I know.
Go ahead.
I guess I'll take the
So
I'll take the
your
point.
idea, he gets to
Your
go.
agreement is wrenching. It's perfect.
This is an MSD blaster coil. MSD is an ignition company that make quite a few high-performance ignition systems of various levels for race engines and high-performance street. I find that this unit very good with production-style ignition system, like a points here or some external coil factory electronic ignition systems. And we'll see if it makes any improvement. I don't have much faith that it's going to improve our high RPM misfire. I think that's occurring here in the distributor, but we will be getting a hotter spark with this coil.
We should probably look at curves, but I think at this point we can say nothing we've done has made any difference whatsoever. It's still a mess.
No, it comes down to the distributor, which we kind of suspected.
Yeah, and we can be confident that it's not the other parts in the ignition system that's causing the misfire.
Yeah.
So
So what we've really showed everyone is that we don't know how to diagnose a problem. We just are parts changers.
Yeah.
even though we said
Yeah.
from the get-go that
Yeah.
the distributor is probably floating the
Yeah.
points.
Here's what's really going on right now. Throughout this testing, at the very high end, you've heard this engine misfiring horribly. And from the very first time it did that, both of these guys claimed the points are floating, which means the points inside the distributor are what open and close in order to send spark to each cylinder, and they ride on an 8-lobed little camshaft in there. And if the spring that holds them closed is not working properly, basically they'll float like a valve spring. They'll lose control and it'll send spark at the wrong time. And that's probably what's going on here. And so we need to fix that before we keep our testing going on. So let's admit that for whatever reason, the points are junk at this point. I think the other problem that we have is that we know that the timing curve in this points distributor is slow.
It's a little lazy.
We looked at it with a gun, and you can see that all of the timing lead is not in until 4,500 RPM. So while normally we don't worry about an ignition timing curve on the dyno at all, because typically performance curve would have all of the ignition lead in by 3,000 RPM, this one is slow enough that it's not all until 4,500 RPM. So if we make a distributor change, we're going to see a difference in the power curve just from the ignition timing.
Yeah, potentially at the bottom, but I mean, these distributors are not easy to get to change, you know, the curve or to even get to the springs so it comes in faster. You know, I think it's fair to say that this distributor was designed for some sort of Ford-powered motorhome or pickup truck,
yeah.
and that's what you want there is, you know, the curve to come in late at 4,500.
So basically what he just said is, we're going to make two changes at once, which is switch to electronic ignition, and it's going to change the timing curve at the same time. So we're going to expect to see a little bit of a different shape of the power curve down below 4,500 RPM. Anything above that, we're going to credit towards not having ignition points, right?
Yeah.
Okay, so we're going to go with electronic ignition. Are you guys down with putting in an MSD distributor and trying to fire it with a Chrysler box so that we don't have an MSD multi-strike box on it?
I think those Chrysler boxes are pretty good, actually.
Okay, so electronic ignition, here we come. All right, out with the points distributor. The MSD distributor is going to have different plug connections here. We might end up having to change wires at the same time. It'll be kind of a big swap. We're going to change the timing and the triggering method and the spark plug wires all at the same time. Scientific testing, out the door.
Here's a quick rundown on the Mopar electronic ignition control box we're going to run. We're using that instead of the MSD because the MSD is a multi-strike box. In other words, you get more than one spark at low RPM especially. And we just want a conventional electronic ignition control. And we'll have this thing wired up and running in no time flat.
We made it Ford tough with Mopar stuff.
I'm happy again because it works.
I know, I was done with that misfiring.
Yeah, me too. I was just getting to the point where it was just, you know, you can only take that so long.
What kind of power are we making now? Wow, okay, we finally have an engine here. We made 636.9 pound-feet of torque and 626.4 horsepower. We're obviously not having the problem with misfire clear up at the top end.
Finally.
Can we compare this with the points curve just to see what was going on down here?
Boom.
Wow. Interesting. So black lines are with the electronic ignition and red is with the points. What's weirding me out is that we're not seeing any difference here due to the ignition timing curve. So I guess ultimately the deal with the timing curve is that it wasn't that different, and I thought it was. But the other lesson here is, wow, junk wires, fouled plugs, points distributor, ancient coil, made basically no difference below 4,000 RPM.
Yeah, I mean, if it's firing and it's on time and it's getting there, you know, you don't see a lot of change.
But all the difference is going to be in, I think, cold start, longevity of all the components, you know, not having to tune it up as much. What I'm saying is the points versus the modern parts that we just put on, there's still benefits to it. It's just we're not seeing it in this test.
Oh, yeah, there's no comparison. I mean, you know, there's a reason that all of that stuff evolved way back when.
I think now we're ready to make big power.
How are we going to do that, Freiberger? What's left?
Oh, we're going to go get the guaranteed performance spark plugs.
Ooh.
Okay.
Okie dokie. So next thing I want to do before we actually put an MSD multi-strike box on it is try some of the spark plugs that are advertised to make more power.
Okay, I'll get some changing plugs.
Okay, hold everything. I told you that we were going to change spark plugs and test those. So many times on Engine Masters off camera, we'll do a bunch of testing that you don't see. And it's not that we're testing new stuff that you're missing out on. It's that we are rebaselining and we're just looking at things and looking at all our temperatures to make sure that we're being fair to the product that we're testing and that our data is accurate. So in doing that, we found out that this ignition box is junk. So we set this thing back to our initial baseline and we were testing this box, and every time we made a pull, the power was just coming down and down and down to the point where it finally had a misfire at the top end. Now, Steve and I have seen that these Chrysler boxes are notoriously unreliable that way. So we ran to Napa and we bought their brand of chrome box here and we ran it and poof, Problem solved. And so we're gonna run outside right now and I'm gonna show you some of those dyno curves that show how the orange box was falling apart and how the chrome box there recovered it. And after that, we're gonna put the MSD box on it and see if that makes even more power. Okay guys, I told everybody what happened. Junk. So check it out. These lines are both with this orange Mopar box right here. The black line was earlier in the day. And then as we started testing those plugs and then rebaselining them and everything, it was getting worse and worse. You can see at the big end, it started to misfire right there. And Steve just pulled out of it because he's tired of watching this big black Ford shake his dyno apart and backfire and stuff. But it got that bad. And then we put that new Napa box on it and fixed. Can you show people that?
Wow.
Wow. Okay, so to be clear, the black line here is the best case scenario with the orange box. The blue line is when the orange box started to fall apart. The red line is that new silver colored Napa box. That's a big difference from two items that look exactly the same, and that if you hadn't hit that misfire up there in the car, you would never know the difference. And I think the only real lesson here is that this stuff is inconsistent and unreliable.
It's completely Russian roulette. You get a good one and you really want to hang on to it when you're running.
I know. So I guess the last step is that we're gonna put an actual MSD multi-strike box on it and see if it solves that and makes more power. Is it a digital 6A? What are we gonna run?
It's a digital 6A. 6AL2.
6AL2.
The actual designation.
Yeah, so pretty standard stuff that a lot of
Yes.
these guys would have on their car.
Yeah.
MSD, here we come. Okay. How are we gonna make this happen? Just unplug junk and replug junk?
This is the simplest thing you've ever seen.
That's it?
Plug that in, and I will plug that in.
Oh, we're not using this coil anymore
We
either.
are MSD'd.
So which coil are we actually running off of? That little e-coil guy. Okay. So just like that, we changed to that MSD digital 6AL2 up there and also the MSD little epoxy coil. We're no longer running the blaster. This better work because I'm at my limit of stuff not working. Oh, what a relief. So sick and tired of messing around with things that spark. Our final numbers on our 514 big block Ford are 648.2 pound-feet of torque. Look at that monster. I mean, from 3,700 all the way up. That's a beast. And our peak horsepower, 633.2, which we haven't seen so far today. And look how it ran all the way out to 6,500 RPM. And I didn't even hear it beginning to break up before.
I just wanted to prove a point when I did that. It's like, run it another 500. It's not going to misfire. It's going to be good.
Yep. Okay, what should we compare this to? I don't think it's fair to compare to the first test when we just had radical misfire with those spark plug wires.
No, not at all.
But let's go down to the good Autolite spark plugs, the $18 spark plug wires, and the points ignition, just to see how far we've come. That will be a comparison of brand new good parts to brand new good parts.
Right.
Just brand new junk good parts to brand new good parts.
This would be the wires and the points ignition with the original coil.
Let's see. Wow, that's a big deal right there.
It just shut off.
Yeah.
Basically.
Yeah, I remember that. It was jumping off the dyno. I hated it.
Wow. I mean, not only the RPM carry radically farther, but this is significant. What's the difference in this data point and that data point power-wise? From 628 pound-feet to 647.5. 20 pound-feet.
You'll feel that
just
in the car.
from ignition, for sure. And, you know, up to here, if you just listened to the thing or drove it up there, you'd go, this car's fine, runs good, right?
Absolutely. And then, yeah, I mean, you can see the dips and the drop-offs and the misfires and...
And the frustration just trying to hunt it down because you're thinking, is it my distributor? Is it my control unit?
it
Are
valve
my
float?
points? Oh, yeah, it could
Yeah.
be valve springs. Maybe my carburetor is messed up.
Yeah.
So,
Yeah, you hear guys all the time, they'll text you on social media, can you help me troubleshoot this thing? It falls apart at 4,000 RPM. Like, well, it's a smorgasbord of dilemmas, but there you go. That's a big difference. That's a big, big deal.
So do ignitions make a difference?
At the beginning of today, I would have told you no. Like he kept on saying, if it sparks and fires it, it can't get any better.
well, I can tell you this. You could take any one of these ignition systems. You could take the Chrysler one, and you might have that great chrome or gold box from Mopar back in the 1980s that was really super high quality, race quality stuff, and dial in that ignition system and make it your life's work, and you can get a darn functional ignition. And you can do that with points too, to an extent. But or you just save yourself all that headache and get good stuff right from the get-go and make Brule happy, right?
You know,
look at that grin.
That kind of grief is just not worth $500 or $600 when you can get a distributor, a box, and wires for all of that. It's just, I mean, it's just too frustrating.
Okay, Brule, I've got good news for you. We have another episode we got to do tonight, and you'll see that next time. Meanwhile, Dulcich and I are going to go wrap this up. Well, Dulcich, I believe that you and the audience have witnessed the exact moment that I can no longer be a points-loving troglodyte.
Oh, no.
It's over. But cannot be overstated how great the big block Ford was. I mean, 650 pound-feet forever.
Freiberger, I think I'm in love with the big block Ford.
With electronic ignition.
Oh, yeah.
It's a landmark moment, ladies and gentlemen. Dulcich becomes an actual, somewhat modern ignition guy, you know, stuff that was invented in 1974, and a big block Ford guy. Pretty good. Life-altering experiences on every episode of Engine Masters.
That's the beauty of an analog device. You know, if that was digital or had a touch screen, it would have been in a landfill a long time ago. But that has analog knobs and a gauge. So it can sit in your toolbox for 25 years, right, Steve-O?
No, this thing is like 45 years old.
That's
this
awesome.
is pretty cool. Isn't it cool?
Yeah, my brother got me one for my birthday. He found it brand new on eBay.
Yeah, so yours is a collector's item. Mine's a tool in use.
Oh, I used mine already.
Hello, xin chào tất cả các bạn nha, lại là mình đây. Lại ra cũng video hay cho các bạn xem. Các bạn thấy hay thì hãy like và comment cho kênh của mình thật hay nhé. Cảm ơn các bạn đã theo dõi kênh của mình. Thank you các bạn rất nhiều nhé. Ok, thank you. Ok, thank you các bạn nha. Số chi. Hai đổ sang nha. Hơi anh cứ cầm đấy. Bật thổi tạ cái máy. Cầm lấy anh. Ui giời. Chuyện thật. Tưởng là 6, 7, 8, 9. Nhìn tờ tiền cứ tưởng 6, 7, 8, 9. Mai làm tí phở. Khách của họ chạy giờ họ đi taxi thì đông phết nhỉ.
Nhà nghỉ không đi bảo họ bộ đần. Mình lại là làm. Siêu không có lên trên đủ cứng rồi sang lên. Khách sạn ấy mới mở với lại ấy kia bị bảo ấy. Nhà nghỉ kia.
Chi cappuccino Rang cắm trực mãi ở chỗ tối. Xin chào, hẹn gặp lại các bạn. Mình sẽ kết thúc video tại đây. Cảm ơn các bạn đã theo dõi kênh của mình. Thank you các bạn rất nhiều nhé.